Everybody. My name is Stephen Mark Williams. I'm the Executive Director of the Energy Technology Partnership, ETP, and I welcome you all to this event, the first session in the Energy Innovation Emporium webinar series. So today, Monday the 10th of May, and it's just after 1:10 here in Scotland. And this series basically highlights Scottish capability, research expertise that will help deliver COP26, assuming that it will still take place in November here in Scotland. Certainly we seem to have the pandemic under control at the moment, so let's hope that it will go ahead. So anyway, welcome everybody. So specifically this session is accelerating the contribution of ocean energy to net zero. Certainly, of course, Scotland, surrounded as it is by ocean, has a long and distinct history of developing energy technologies for the sea and for the ocean. So today's session will be based around that. So today's speakers, they will be presented them more formally later, but we have a good selection of speakers here today, both from academia and from industry, and also from, you could call the third sector knowledge exchange. And just to give you the background of the Emporium, so the Emporium has actually been running for 4 years now. This is the 5th year, but because of the current situation, instead of having it as a one-day conference, we decided to split it out over various sessions that last between now and COP26 itself. So there will be a session every 2 weeks. So I'd invite you to go to the ETP website and register for these. So we have a whole host of different hosts. Wave Energy Scotland today are partnering with us, but in 2 weeks' time, for example, we have the Scottish Rural College. They'll be presenting around agriculture and land use. We have Construction Scotland Innovation Centre. We have the Energy Systems Catapult, the Offshore Renewable Energy Catapult, Zero Waste Scotland, and SALSA. SALSA are our partner research pool in life sciences. ScotChem, the National Manufacturing Innovation Centre, Data Lab, MAS, and the Scottish Government. So all of these organisations are partnering around the Emporium this year. So that's good to know. So just a little bit about ETP before we move on. So ETP is the alliance of 13 Scottish universities. So we've been going for about 11 years now. So here we are. So this is an informal alliance of universities that have world-class capability in energy research. And our job is just to make sure that we make the best of all the research that's going on by fostering and helping collaboration, not just between the universities and the academics themselves, but also between the universities and external agencies such as the government and industry. And so we endeavour to increase the impact of research through the collaboration. So we have around 200 academics and around about 700 researchers involved in this. ETP is one of 10 research pools, academic research pools. So we're the energy one, but there's also engineering, life sciences, chemistry, physics, and others. So again, their job was supported by the Scottish Government, and our job is specifically to increase the impact of academic research. So a couple more things then whilst I'm here is I'll just discuss the Energy Industry Doctorate Programme for you a bit. So the Energy Industry Doctorate Programme is a great opportunity for industry to engage with academia and to transfer and exchange knowledge, to work together on projects around doctorate, so around PhDs eventually. So projects are developed in the energy sector. So at the moment we do have a call open. If there's any industry out there interested in engaging with academia, not only interested in engaging with academia, but of course also developing the relevant skills through a doctorate for a researcher to come and maybe eventually work for your company. So the program is open right now. So it's a collaboration between academia and industry. And the point about it is ETP will fund up to £30,000 of the doctorate. Okay, so doctorate would normally last between 3 and 3.5 years, depending on what it is. but ETP will fund up to £30,000 of that, so depending on what the project is. We have so far funded 127 doctorates across all themes, so wind, marine, carbon capture and storage, oil and gas, any kind of energy, then we will open to fund. And we also fund any company, any size, anywhere. So the actual program itself, a doctorate, is a collaboration between an industry sponsor and an academia. So the industry sponsor can be any size, any location, and indeed I would say about half of our industry sponsors are international, and about 80% of them are probably large companies. And you can find a full list of projects on the ETP website. And the deadline for this particular call is 12 noon Friday, the 11th of June. So you have another month or so to get a collaboration together, but there will be another call open immediately after this one, which will then close in 9 months' time. So you have an opportunity, if you happen to miss this call, to get the next call in. So that's the end for me. So does anybody know if Jim is on the line? No, okay. Right, in that case, can I suggest that we move on to the next bit then? Jonathan, do you want to show yourself and introduce yourself?
Thanks, Stephen Mark.
Okay, so Jonathan will lead you through the rest of the program for today. So Jonathan is with Wave Energy Scotland and engineering specialist, I guess you would say. So Jonathan, over to you.
Thank you very much, Stephen Mark. Let me just share my screen. And Stephen Mark, if Sir Jim arrives, will you bring him in?
Yep.
You will. Okay. Just share my screen. So thanks everyone for joining us today. As Stephen Mark says, my name's Jonathan Hodges. I work for Wave Energy Scotland as Senior Innovation Engineer. And the topic that we're covering today, all of these webinar series are all in the build up to COP26 in Scotland. So we've chosen the title of Accelerating the Contribution of Ocean Energy to Net Zero. And I've got a really great panel of speakers to join me to discuss that topic. First of all, I'm just going to talk about the opportunity for wave energy and tidal stream energy in Scotland, commonly known as ocean energy. And I'm kind of expecting some people who are very experienced in this sector to join us, and perhaps some who are newer to it. So we're going to keep it fairly high level. I'm going to introduce the opportunities for ocean energy in Scotland, set a scenario for deployment of this technology in the coming years, and then talk about what innovation is going to be required and is currently being delivered to achieve those targets, those deployment targets. Then we're really lucky to have Jan Hervé de Ruyck with us, who's from France Energy Marine, but also the chairperson of the International Energy Agency Ocean Energy Systems Group. He's going to give us an international perspective. Then Andrew Aviard from Edinburgh University, from Edinburgh Innovations, talking about the capability within Scotland from a research infrastructure and research perspective. Then James Murray, Programme Manager of Orbital Marine Power, talking to us about the exciting state of their technology development and upcoming deployment. And similarly, Cameron McNatt, who's founder and managing director of Mocean Energy, they're talking about their activities and upcoming exciting deployment.
Jonathan, just to make you aware that Sir Jim has entered now.
Carry on.
Okay, so Sir Jim, can you hear me?
Yes, I can, Stephen Mark.
Great, Jim. Thank you very much for attending this, Jim. I'm sure you've got a very busy schedule today. So we're up and running with the event, Jim. So if you have any few words. So just to introduce Professor Sir Jim MacDonald is the chair of ETP and also the chair of SRPE, two of the Scottish research pools. And I'm delighted to welcome him to say a few words to us right now.
Right, Stephen Mark. Jonathan, forgive me for interrupting you. That was not my intention. I was slightly delayed in joining you, so forgive me for that. And I won't delay the proceedings much longer, Stephen Mark, other than to say a very warm welcome to those that are participating today. The fact that you and the team, Stephen Mark, are delivering this Energy Innovation Emporium 2021 webinar series is very timely. One, it's great for the ETP, one of the highly performing pools to engage and step up like this. But of course, as we know, and I'm sure it will feature regularly through the contributions this afternoon, given that COP26 is almost upon us. We're becoming all the more excited about it. A colleague of mine whom you'll know, Sir Patrick Vallance, who's the government's chief scientific advisor. Patrick was telling me and a group of other, I'm president of the Royal Academy of Engineering, he was telling myself and Adrian Smith and others last week that it's likely there'll be a secure day for science, research and innovation with there'll be a dedicated space for that as well. So ETP I expect to be involved, but the build up to it is key. And looking how Scottish research and innovation capability can map into delivering international and regional climate change target deliveries. So conversations like this are absolutely key. And very often, colleagues, as you know, we collaborate better when we're talking to each other regularly. So this webinar series that you're engaging in, it's working with the pools with Research and Innovation Scotland, which is a collective grouping of the Scottish research pools and innovation centres. And there's a broad programme, but we are, as ETP, presenting this series of webinars demonstrating how Scottish excellence in research and innovation and its ability to connect an international community can really make a difference to global energy strategy, delivering carbon emission reduction targets, especially around, as we know, through what COP26 and the UN is driving around nationally determined contributions. We've seen recently the Prime Minister in the UK bringing forward targets of 78% reductions by 2035. Scottish Government maintains its commitment to net zero by 2045. Cities like my own in Glasgow showing a big, bold commitment to net zero as we approach 2030. But in all of this, it will be down to people doing the right things, working together, mapping research and innovation, educating great talent, and then focusing on outcomes that will make all the difference. And that's what ETP does naturally. So I know that the series will be covering all aspects of sustainable energy, from ocean energy to looking at future energy scenarios, and from agriculture through to land use to biotech and all points between, including renewable energy. So, Stephen, Mark, without me delaying any further, apologies for coming in late, but I did want to take the opportunity to thank you and the team for delivering this, for all those that are participating, and I look forward to hearing of the outcomes as they roll out over the course of the running of the seminar. Thanks a lot, Stephen, Mark, and I'll let you get back to your audience.
Okay, thank you very much, Sir Jim, and I look forward to having a coffee with you in the Millhouse sometime soon.
maybe that's days away rather than months, Stephen, Mark. All the best.
Cheers. Okay, thanks a lot, Sir Jim. Okay, Jonathan, back to you.
Thanks very much, Stephen, Mark. Thanks very much, Sir Jim. We are going to start, before we get into the presentations, we're going to start with a short video that's been produced by the International Energy Agency Ocean Energy Systems Group. We're represented by Jan Hervé shortly, which is a really great introduction to the ocean energy sector for those of you who are new to it. So Syra, if you could play, that'd be great, please.
The ocean is vast, and the potential for countries to benefit from its energy is immense. Ocean energy contributes to the world's sustainable development as it reduces dependence on fossil fuels and mitigates the negative impacts of climate change while generating jobs. A source of energy essential for the economic development, sustainability, and quality of life. As well as supplying utility-scale electricity, it can be used for different applications, including the production of drinking water, and is a great opportunity for islands and many countries that rely on oil imports for electricity generation. This is still an emerging industry. Installation and operation in an open sea environment pose significant challenges to the sector. Therefore, through international collaboration, excellent progress is being made to ensure that ocean energy becomes competitive with other energy sources. Diversification of renewables is needed to meet the decarbonisation targets of 2050. The OES, a technology collaboration program of the International Energy Agency, presents a common approach that encourages the development of the sector, seeking a significant improvement of economic and environmental outcomes. And it invites all: governments, agencies, research organisations, knowledge centres, companies and individuals to engage in strategic development and innovation activities, formulating supportive policies for the development and deployment of large-scale ocean energy systems, making it a cost-effective and reliable low-carbon source of energy generation for the whole world.
That's great. Thank you very much, Sarah. I'll share my screen now. Okay, there's been a few people joining since we started, so I'll just very briefly run through the speakers that we've got today. I'm Jonathan Hodges from Wave Energy Scotland. I'll start with a high-level summary of the opportunity for ocean energy in Scotland and set a challenge for the innovation that's going to be required to achieve those deployments that contribute to net zero. Then we're going to have Jan Hervé de Rook, who's the chairperson of the OES. You just saw their video. He's going to give us an international view of the sector. Andrew Aviard from Edinburgh Innovations is going to talk about the capabilities within Scotland in research infrastructure and research capability. Then we've got James Murray, Programme Manager from Orbital Marine Power, talking about their technology and their upcoming deployment in Orkney. And similarly, Cameron McNatt from Mocean Energy, who's going to talk about the Mocean wave energy technology, which is also on its way to Orkney. So this is where I want to sort of set out a scenario for how ocean energy is going to contribute to net zero targets. Starting off with a high level look at the opportunity for ocean energy in Scotland, and then setting this scenario. And it's that scenario that will look at how Scotland's responding in terms of supporting innovation, supporting technology development and deployment in Scottish waters. And then alongside those support activities, how is Scotland collaborating both internally and internationally to help accelerate that activity? And then we'll see how the technology developers have been able to engage with that over their lives. So ocean energy in Scotland. We really do have a really significant ocean energy resource in Scotland, with up to 25% of Europe's tidal stream energy resource, 25% of offshore wind resource in Europe, and 10% of Europe's wave energy resource. So a huge opportunity for deployment of these devices, of these technologies in Scottish waters for generating clean electricity. But also alongside that, once we develop that technology, a huge export opportunity. And it's that resource that's led to Scotland over the last few decades taking a world-leading role in terms of research capability, technology development, and deployment of devices. And the deployment of those devices is really focused around the European Marine Energy Centre. And we will no doubt see a lot of discussion about upcoming deployments at EMEC, which has really been a massive support system for the development of the sector in Scotland. But there's increasing competition. It really is becoming a global sector, and anyone that was able to attend the International Conference on Ocean Energy, IEA, a couple of weeks ago, can really see how this has turned into an extremely international sector and a great opportunity for export around the world. So I mentioned some imminent deployments, some really exciting pictures coming out recently of large-scale machines being constructed and taken up to the European Marine Energy Centre, ready for deployment. And in tidal stream, we've got Orbital Marine Energy with their latest device, the Orbital O2. James is going to tell us about that. In wave energy, we've got both Mocean Energy and AWS Ocean Energy coming to the end, having completed construction or coming to the end of construction of their wave energy devices, ready to go to Orkney for testing again at EMEC. And those are really exciting pictures that everyone's been seeing recently of large devices either being towed or being taken by road up to Orkney. But inside those technologies, there is a huge amount of, inside those devices, there is a huge amount of technology, supporting technology and subsystems, which has been developed a lot of which has been developed in Scotland through various support programs. So it's a really exciting time in the ocean energy sector. We're about to see things being deployed in the water that really will hit mainstream news, and it's an exciting time to see that happening. So then I said I wanted to set a deployment scenario, which effectively kind of describes the challenge that these technology developers are responding to. And I'm going to use a piece of work that's come out of the European Commission over the last few years, which is called the Strategic Energy Technology Plan, which is basically a set of activities and an overarching plan to lead the clean energy transition in Europe. And what they did recently is to set a series of cost targets for the levelized cost of energy of ocean energies and what they need to achieve by 2030. So they set targets for tidal stream of 100 euros per megawatt hour and wave 150 euros per megawatt hour by 2030. So those might seem like quite challenging targets, but what I'm going to use to set this scenario is a piece of work that was done by the University of Edinburgh along with the Energy Systems Catapult. And what they've done is taken those costs and they've used an energy system model which looks at the cost of energy, the levelized cost of energy, and says at that cost and with the competition delivered by all of the other methods of electricity generation, what amount of deployment, what installed capacity of deployment would we expect as we move into the future to be taken up by each of the different technologies. Effectively, it's how does a generating technology buy its way into the energy system. So what the University of Edinburgh team with Energy Systems Catapult have done is create a number of scenarios where they vary the competition from nuclear power, being one of the big variables in the system, depending on how many new nuclear power stations are going to be built. Then they say, if we achieve those set plan cost targets on the slide there, if we surpass those targets by 20% or 30%, then how much ocean energy technology, how much tidal stream and how much wave do we expect to be deployed in the UK? And you can see some very small graphs on there, seeing the deployments building up into the future. And you can see that depending on the competition from nuclear and depending on the cost achievement, we start to see wave and tidal energy being deployed at significant capacities onto the system by 2035 or 2040. And then by 2050, for the whole of the UK, we're looking at 10 to 15 gigawatts of tidal stream, 9 to 17 gigawatts of wave in a low nuclear competition scenario, and then slightly lower numbers in a medium nuclear competition. And low and medium depends, as I said, on how many new nuclear power stations are going to be built. So there we can see that there's a challenge in terms of cost reduction, but also the timescales are suitable for ocean energy to contribute to the net zero targets that governments around the world are setting. And this is the UK scenario. Obviously, there's a massive export potential, and there's a global market being developed to deploy in a similar timescales around the world, and Jan Hove will tell us about that. So that's the target we're trying to achieve to contribute to net zero. But achieving those set plan targets demands innovation. I've highlighted again the 2030 cost targets, and what we need to do is continue innovating to come down from the costs where the sector currently is to achieve those targets by 2030. Now, this is another piece of work by the University of Edinburgh, where they look at what innovation is going to be required to meet those targets. And it's very difficult to get a standard number for the levelized cost of energy for wave energy, for tidal energy, because it's a very early stage in the sector, small numbers of devices being constructed, but also a large range of different technologies being developed. So this was a comparison of those set plan targets against what we think are the average costs that are being developed in the market at the moment. And what you can see from this table is that if you divide out all the different cost centers of a large ocean energy device into development, infrastructure, some of the key components such as the structure of a device, the power takeoff, which converts from movement into electricity, then most of the areas are demanding innovation to achieve their targets. And this is if we carry on with standard innovation, which are sort of standard learning rates through through learning. But what we can also do is to move into the world of advanced innovation, where we start to achieve higher learning rates of 10 to 20%. And there we can see that some of the wave and tidal subcomponents and subsystems are effectively on track for delivering those cost reductions, but innovation is still required. And that's exactly what Scotland's doing, and that's exactly what we want to showcase to you today. So we're looking for advanced innovation, and that's exactly what we're delivering. So in terms of innovation support in Scotland, we've been very lucky to have consistent Scottish Government support in the ocean energy sector over the years, and that's driven by two big drivers. Clean energy supply, obviously something that Scotland needs and the UK needs to achieve net zero targets. Also, there's a huge opportunity for jobs and economic benefit to come from deployment in Scotland, but also export. And here's two examples of how the Scottish Government's been responding to the innovation needs in the sector. First one on the wave energy sector. Wave Energy Scotland is a great example of a really proactive technology development programme. It's now 5 years into the programme and solidly funded all the way through. And it focuses on some of those subsystems, some of those key themes that I showed in the last slide. Focus on developing the wave energy systems themselves, like you'll see from Cameron, from Mocean Energy, and then some of the key subsystems where we need to remove cost and improve performance and reliability. Over the last 5 years, it's funded many organisations, 230 plus organisations, over 40 million invested on a number of projects around the world, all tested within Scotland and many of them constructed in Scotland. On the tidal side, over the last 2 years, the Saltire Tidal Energy Challenge has been really successful in helping to drive forward innovation and incentivise investment in the tidal energy sector. And two examples there, £3.4 million awarded to Orbital for the O2 floating tidal device, which you'll see more about in a minute. And CIMEC Atlantis, £1.5 million on a subsea hub, which itself is an advanced piece of innovation to help us step towards clusters of tidal turbines and then onto the large arrays, such as the Mocean array planned to continue expansion on the north coast of Scotland. So really strong innovation support in Scotland from the government. And then I just wanted to add a little bit around that. I often talk a lot about the Wave Energy Scotland programme itself, but there's a great network of innovation collaborations going on around the Scottish support mechanism. One of which is the Energy Technology Partnership itself, which in collaboration with some of the development organisations, Scottish Enterprise, Highlands and Islands and Interface, is a great opportunity to make links between Scottish academia and Scottish SMEs, which really supports technology developers as they come into the sector, helping to progress the early stages of their technology development process. Something that we're working on with an international group of companies is DT Ocean Plus, which is a software tool or set of software tools which are intended to accelerate technology development in ocean energy, helping to design, assess and evaluate technologies as they progress right through the development process. Two more things to mention briefly before I move on are Europe Wave, which is effectively another version of Wave Energy Scotland style programme, but run on a European level, funded by the European Commission. And it's a partnership between Scotland and the Basque region of Spain, and is continuing to develop towards 3 large-scale devices being deployed in both EMEC and in Basque Energy in the Basque region. And finally, at the top right-hand side, an example of collaboration is a document that OES has published recently, helping people understand a consistent development path for ocean energy technology so that all countries around the world can make effective and efficient decisions on who they fund on the technologies which have got most chance of commercial success. So that was a quick run through the Scottish opportunity. I've presented a target that needs to be achieved in order to achieve a certain scenario of deployment, and now looked at some of the support mechanisms we've got in place. But I'd really like to now pass over to Jan Hervé de Rook, who's the chairperson of the IEA OES, to give us an international view of what the ocean energy sector looks like. Jan Hervé, are you able to share your screen, please?
Yes, I think I am. Thank you, Jonathan. Can you see me? Can you hear me?
I can see you and hear you.
Great. And now I'm trying to launch also, if I put that this way, share screen, and I should be able to share this screen only. Is it right?
That's great. Thanks, Hervé.
Great. Okay. So thank you very much, Jonathan, because you already quoted a little bit what we're doing at OES, and you also quoted a little bit what I'm going to say. But so you invited me to give an overview of to give a global view, and I think I will do it. So in this position of chairman of the OES, quite recently. It has begun last January. So the first thing is maybe just to say what the IEA OES is all about. I mean, it's one of the technology collaboration programs under the umbrella of the International Energy Agency. And there's a couple of these technology collaboration programs which deal with renewable energies. It's not only renewable energies, as you can see, but among these renewable energies, you have some on PV, hydropower, wind energy, biomass, geothermal, etc. But at OES, we're dealing with ocean energy systems. And so the idea is really to have international groups of experts that work together and to accelerate. The dissemination of people have to know about these technologies. And presently we are 23 countries plus the European Union, and representing these various countries. It's among diverse parts of whether governmental departments, industry association, research organization like myself. So I'm head of France Energy Marine, which is a public-private institute in France devoted to offshore renewable energies, but you have also energies, energy agencies, etc. And of course, the idea is really to be this international voice on ocean energy, and to accelerate, so it's say, the viability, uptake, and acceptance of ocean energy systems, and which is something which is really important. It's in an environmentally acceptable manner. Sorry, I'm not going the right way. So ocean energy, although I think I couldn't attend from the very beginning of this afternoon session, but I think you mostly talked about tidal on wave, while it encompasses something a bit larger, because you also have thermal gradient, the so-called ocean thermal energy conversion, also salinity gradient, and with tidal, not only in fact energy that can be converted from currents, but also from the tidal range. And there is a vision behind that, is that worldwide there is this potential of developing over 300 gigawatts of ocean energy by 2050. And as also Jonathan mentioned, this goes also with jobs. The last assessment we have is about more than 600,000 of jobs that could be related with this development of ocean energy systems if it goes up to this point. And also, of course, we are talking about renewable and decarbonized energies. So there's also an assessment of the number of tons of carbon dioxide that can be saved. The thing is, so just back here, so offshore wind is not within the ocean energy systems, and also the products, that's something important. Products is not only electricity conversion of the energy into electricity. It can be directly heating or cooling. You have the seawater air conditioning system. You have heat pumps directly from seawater, and also the product can not be just electricity, but for instance, the production of fresh water, so desalination. And in this framework, you can understand that it's also way of using at best these ocean energies, especially with their intermittency. That's something which in many places can be an issue. So electricity also, it's not just at the utility scale grid, so the big continental grids, but also for islands, so smaller grids, local grids, and where, and I will stress a little bit on this at the end, there are many challenges, and it can be very, very interesting. Another market which is also developing a lot, which is the one of the offshore industry, when you need also so power outside of the grid for any other kind of products. One of the big developing sectors is aquaculture, and what you see on the picture on the bottom right is, for instance, an aquaculture system coupled with wave energy in China, and that's something that is already tested for more than 18 months. And of course, today it's only within one of the circles there, you have the production of green, so then let's say blue hydrogen, directly from ocean energy, which is also one of the solutions for energy storage. But what we have to really admit is that there are several issues that have to be tackled, and the first one is the cost reduction. I think, sorry, you can't see me very well. Sorry, cost reduction. We are in competition, in fact, with all the energy generation options, let's say, all other kind of renewable, or not renewable, but let's say renewable. And we really have to demonstrate that ocean energy, although there is this huge physical potential, can also be economically a good option. And so when we write that these challenges are similar to those faced by offshore wind, it's a question of a couple of years after, and Jonathan also gave figures about the cost of energy for offshore wind. It's actually lower than the one for ocean energy, but still high. There's been, especially in Scotland, as you know, many prototypes that have been tested at sea. And however, the thing is, what we have to address is really the reliability and the survivability of these systems. And this is something that we have to enhance on all components, and we will a little bit look over the various components. And the last point, which also goes with cost reductions, of course, but it's really to get the best performances. And so it's to improve the efficiency, the performance, the load factor. It's a trend also that we've seen with solar and especially with wind to have always a higher R factor, so load factor, and that's something that we can of course expect also for ocean energy. That's to say also to be able to harness energy from less and less powerful currents, but get to be efficient, however. And that goes with also enhancing the operability, the access for servicing, and the global availability of the system. All these things are very, very important. About the cost reductions, so many analyses have been already performed. The first one is kind of chicken and egg question with the manufacturing at scale. So you can't have a big scale as long as you're not with a low LCOE, but you won't get a low LCOE as long as you're not manufacturing at a large scale. So but there are other also questions like really breakthrough in the design and like also convergence with respect to given shapes or principles, like it's going on a little bit on tidal, where horizontal axis turbines are becoming the one that are the most relevant these days. The standardization of components is really important, and among the components, the power takeoff, the foundations and moorings, and these are places, foundations and moorings, where it can be shared, for instance, with floating offshore wind, where many things, and also, you know, like umbilicals and things like that can be shared. Of course, to have to get better modularity by deploying the systems in array, to as long as we get experience, becoming more efficient when installing, maintaining, and recovering the systems. But also, I think, and that's a point we will see again soon, the gathering data also to improve the reliability and viability on sharing this data. Integration with other technologies, I will talk about it a little bit later again. To get better performance, have a finer resource analysis, and also be able to forecast better, to be able to sell the energy at the best price, and to improve also the grid and network connections. And as you see, while you have learning curves that have already been assessed of what it could be with the cumulative deployment for wave and tidal. And as it's been said already, it's getting a little bit better for tidal than wave, a little bit earlier, but still much effort has to be performed. The various areas where development can occur are, of course, on the structure itself and the prime movers, like, of course, the blades or the rotating systems or moving systems. Foundations of moorings, like I said already, power takeoff and control systems to enhance the systems, like it's been done also for offshore wind, as you know. All these questions of the array system and subsea connections, whether should it be wet mate or dry mate connection, and also all these issues of installation, maintenance, and recovery. But we will gain on this if we allow the transfer of knowledge and of technology as much as we can. If we set up as early as possible standards or pre-normalization thresholds, like I will quote it again, but Jonathan said it, this guidance, framework guidance that are very helpful in getting into this pre-normative process. And also encourage as much as possible the collaboration between competing device developers so that they will design common components and that will, of course, have an effect on the LCOE. So I won't get through all these points here, but the technological challenges are numerous. And also, if you look at the sketch on the right, it's like a loop. I mean, you're developing the device and systems, so it comes from subsystems and components that are also have to be developed up to the point that there will be a commercial deployment, but you get the first figures of what it's really actually costing, and you're really entering the competition. And from this, you can go to the optimization of your design, and use tools like developed in DT Ocean, like Jonathan was mentioning, in order to optimize these things. And this is really a loop, an infinite loop, because even in the automotive industry, you wouldn't say that there's no innovation anymore. There's still research that needs to be done. So that's the way it should be looked at. And when we were talking about technology transfers, here are, I mean, already a synthesis of the most of the closed sectors where with whom the technology transfer should occur. We of course think of oil and gas, or the offshore industry for oil and gas, and also offshore wind and renewables. That's quite obvious in shipbuilding. But there are other places where, in fact, if we are dealing with the same kind of schemes, we can gain a lot. And especially with the rigor that you find in aerospace industry or in robotics, and we can gain a lot with new materials for the prime movers, for the PTOs, for all these things. That's quite obvious. Okay, just a few more slides just to talk a little bit again on Ocean Energy System technology collaboration programs, just to let you see that we are working on many of these topics together. So we have 12 tasks that are presently running concurrently. And what we are producing are reports, and one of the most famous one, I said it at the beginning, but I didn't recall it, but it's really the environmental integration. That's something quite very important, because it's a new industry at sea, and we really have to give evidence that it's done in an environmentally friendly manner. So there's this state of science report, which is edited every 4 years and updated. And then a couple of reports, one on the ocean energy in islands and remote coastal areas as a specific market. Another one on the blue economy and all this offshore industry I was quoting. And again, the report Jonathan was quoting about the guidance framework to assess the level of maturity of systems in a manner that is really shared by all of us. Then we issue an annual report. From this, we also edit highlights, a specific one on wave energy developments, another one on tidal energy developments, and these are the main things that we are producing. These are the most recent one. I think I don't have time, Jonathan. I think here was a couple of slides, and I don't know if we can share the slides afterwards.
Yeah, I'm sure we can share the slides, and perhaps we can catch some of that stuff in the discussion at the end. I think you've done a good job of introducing some of those other opportunities alongside electricity generation at scale. So that's something that I think the others will pick up on.
Okay, so just to say that for instance, for the specific market on islands which are not grid connected, we have performed the analysis of what are the conditions for which this can develop in a proper and short-term or mid-term manner, and that's really important. These are not just technology issues, but also the kind of support that you can get, and also how the sociological issues can also be taken into account. Okay. So then I come to the summary, which is okay. There is a huge potential which has already been assessed. It's a physical potential, but it's also a technological one. And what we really have to really face and look is to recognize that there are some technological issues but moreover, there is really this question of accelerating the decrease of the LCOE, which is the key issue, taking into account the fact that there are many markets with many paradigms. There is the one at the utility scale where maybe the goal seem a little bit far away, but more accessible ones are the ones of for the non-connected islands, and also for the offshore industry. Thank you very much. Just to say again that OES also is producing webinars that can be followed online, but also on our site afterwards. And this is what is the cabinet of the Ocean Energy System right now, and I'm speaking to represent them. Thank you.
That's great. Thank you ever so much, Jan Hervé, for broadening out to the global challenge there and the global opportunity. I want to make sure that we give all speakers a good chance to speak. So I'm going to move straight on to Andrew Aviard, who's going to talk to us about the research infrastructure and capability in Scotland. Andrew, I'll give you a nudge when you're coming to the end of your time.
Okay, thank you. Hopefully you can all see the slides. So I was asked to speak about contribution that academia can make to the ocean energy and contributions to net zero. So I was going to highlight a couple of our research facilities and then pass on to the other guys who will explain how they've gone through our systems. So Edinburgh's spent a number of years now developing its world-class ocean research and facilities, and FlowWave is one of those facilities. I'll go through some numbers just because it's quite impressive. So we have a 30 meter circular concrete basin, 5 meters deep, 25 meter diameter wave and current tank, 2.4 million liters of water. So 2 meter upper test area, 168 absorbing wave makers, 1.6 meters per second max current, 1 meter movable floor, as you've seen, a 5-ton overhead crane, and a 3-minute settle time. So it's a really impressive facility. It was designed to reproduce the coastal waters around Scotland. We can create a full spectrum multi-directional wave and current style. Depending on what scale is chosen, it can correspond to full-scale seas with up to 28-meter waves and currents in excess of 12 knots and a sea area of approximately 2 square kilometers. We can bridge the gap between your kind of flume testing scale and your sea full-size prototype testing. 1/20th scale, you can have a critical stage gate where you can try and move across that, what we so-called the valley of death, from small scale to full prototyping. It offers a unique environment to have unrivaled control and repeatability of the same device, the same test. As you see here, we've done everything from wave, tidal, and floating. We are entirely wanting support. Most of our research is done to support the SMEs, and as you can see here, both Orbital and Mocean have tested within our tank and on their journey towards full-scale testing, which they're doing now. Mocean's a really good example, from their initial proof of concept through to checking the geometries, and then up to testing ahead of the sea trials, as you see now, and looking at the moorings. The second research facility I wanted to mention was Fastblade. Now, Fastblade is still being built. I'll show you in a minute, but it's the ability to fatigue test tidal blades and other composite structures at a really so you can test their lifetime in a much quicker space. So we're looking at testing 20 years in maybe up to 4 months. So we have the ability to test very quickly. It's a novel hydro actuation system which only uses 25% of the energy you put in, because we absorb that into our hydrodynamics. We can test structures 8 times faster than is currently possible. We can reduce the design risk for developers by really providing the opportunity for more and better data sets that maybe to understand what's going on within your structure elements. This will enable more and faster impact. There's research and project development for new advanced materials. The accelerated evolution of specimens will enable more rapid evaluation, certification, and deployment of new products. So you can see here the machine, what it will look like, the units with the actuators. Currently, it's a hole in the ground, but the device is currently almost finished, and that will fit in there. And we're looking to be up and ready in mid-late August. As I say, we're looking primarily to test tidal blades, but we will also look at other elements as well. We're not just working for research, we're working with lots of industrial partners, as you can see. We've also got the Energy Lab, which is a facility to try and replicate the prototypes or replicate the electrical systems that you could use, so that we can look at a full electrical system and model that. In addition to research facilities, we have entire programs. This is the ID Core, where research students do a year in academia learning all the fundamentals of what we required, and then they have a 3-year research program with the individual industrial partner, looking at how they can contribute. The industrial partner gets to choose the project, which helps them. And again, it's all about looking to the individual company to try and help them with issues they have. Again, working very closely with a whole variety of industrial partners. We, as a university, we're based in collaborative research, and we are focused on supporting the industry and looking to encourage collaboration in research so that people can develop their ideas through into real life testing. Now, I'm gonna stop there and a very quick whistle to help Jonathan, but I think that gives you a pretty good idea of all that we're able to contribute at this point.
That's great. Thank you very much, Andrew. And there's a couple of things you mentioned in there, which I can, from my own perspective, see really great collaboration, the ID Core program and also the ETP Energy Doctorate program that Stephen Mark mentioned earlier. Many people coming through those programs and taking up direct roles in the sector and really contributing directly with their research. So there's great collaboration coming through there. Thanks very much, Andrew. In the interest of time, I will pass straight on to James Murray, who's Program Manager at Orbital Marine.
Thanks very much. Just getting myself set up. Can you see that okay?
Yeah, I can see your screen there.
Great, thanks very much. Yeah, so I'm James Murray. I'm the Program Manager at Orbital Marine Power. I'm just going to give you a very brief overview today on our technology development to date, our upcoming plans for the next year or so, some of the collaborations we've had both with the research and academic institutions in Scotland, and how we've essentially designed our technology as well to increase engagement with the Scottish supply chain as well towards the development of our technology. So first of all, we've been developing our tidal technology in Scotland over the past 20 years or so. We've developed it from small scale testing in Orkney right up to to platforms that are over 70 meters long with rated capacities in excess of 2 megawatts. And what really sets our technology apart, right from the get-go, our philosophy was to enable low-cost installation and maintenance with low-cost workboat vessels. So we've got a towable floating platform with retractable legs, and that means that every single device subsystem is accessible on site. And one of the big advantages we have with tidal stream energy, it tends to be located no more than 5-10 kilometers from the land. If we can do all our operations and maintenance with low-cost workboats or even fast rib-style vessels, we can achieve very, very high levels of availability and reliability. So as I said, we've scaled our technology to 70-meter long platforms, 2 megawatt units, but we can similarly scale down our technology to capture more localized tidal and river flows as well. So our most recent test program was of our SR2000 prototype, which was tested between 2016 and 2018 in Orkney. So the technology set a number of industry records. We generated the most peak power by a tidal turbine. That was 2.2 megawatts of power. At regular intervals, we provided around 7% of the Orkney Island's electricity needs. We operated right through the winter storms in Orkney in 6-meter plus waves. And so we learned a huge amount about the hydrodynamic performance of the technology and the power performance of our systems and our generating systems right through those winter periods as well. We generated over 6,000 hours of generation per nacelle, and by the end of the test program had generated over 3.2 gigawatt hours of electricity. Importantly, we had the opportunity to demonstrate our approach to maintenance and installation with a full-scale commercial device. We had over 30 interventions to carry out maintenance on the device, typically on small, inexpensive components, but we demonstrated, again, our philosophy of being able to achieve very fast response times due to that very high levels of accessibility associated with our floating platform. And typically, most of those interventions were carried out with fast rib-style vessels, often on site in less than 45 minutes, to achieve pretty high levels of availability for what was our first large-scale device. And by the end of the test program, had achieved TRL 6 for our technology. So moving on then to what we've been doing over the last couple of years, we have been building the world's most powerful tidal stream energy generator, the O2, supported by both European and Scottish government funding through the Salter Tidal Energy Challenge Fund. We have developed the O2 tidal turbine. Some of the significant enhancements on this commercial demonstrator device, we have 20-meter rotor diameters, which can generate up to about 2.5 megawatts of power and produce enough electricity with each unit for around 2,000 UK homes. We've incorporated pitch control for the first time. We've optimized our retractable legs to ensure that all, that there is on-site access to all the device generating systems, from the power conversion and export within the hull to the nacelles, the pitching units, and to the rotor blades themselves. We've also significantly optimized the electrical configuration and the design for manufacturability. So I won't go into all the innovations, but there's a whole host of innovations in that machine. So the turbine was launched from Dundee, from Texel in Dundee last month, and is now in Orkney. We're doing some tow trials, and it will be grid connected in June for a long-term demonstration and performance qualification program there in Orkney. So moving on to some of the collaborations, both in terms of the research community and further on then into the supply chain. So we've had a number of very important collaborations. We've got a number both in Scotland, the UK, and Europe. I'll focus on the Scottish ones today, both with ETP, but then also with ID Core in terms of researchers. We've tested a number of configurations of our technology at FlowWave that Andrew discussed, both in terms of understanding things like electrical connectors, performance in different combinations of wave and tidal current conditions. So we found that even as we've scaled the technology, the test facility at FlowWave's been actually increasingly pertinent to the types of questions we're asking ourselves from an engineering perspective, particularly when we go to do fine scale optimization from an LCOE basis of our generating systems. We've tested our devices to date at EMEC in Orkney, and we work very closely with them on environmental monitoring. We also work closely with Heriot-Watt on a number of environmental monitoring aspects, including biofouling, for instance. And we've worked with Edinburgh as well, particularly on the kind of the energy systems and wider grid systems modeling to understand the wider business case and commercial case, and I suppose the policy support case for tidal stream energy, capitalizing on the highly reliable nature of the resource to demonstrate the wider grid system benefits. And we're also looking forward to working with the Fastblade facility once it's up and running as well. Moving on then to the supply chain, and I guess opportunities for the supply chain as the industry continues to commercialize and scale up. We've tried to enable the supply chain as much as possible through the design of our tidal technology. This obviously has benefits for us in terms of introducing competition, reducing costs, but also ensuring that we can work with the existing supply chain as much as possible, which will be very important for scaling up the technology and for enabling supply chain capacity through particularly the early years of the scaling up of the industry. So we've developed a platform technology that is, each of the sections are very much road transportable. So we've been able to use both inland and coastal locations for fabrication of the platforms for the O2 tidal turbine. We've reduced the draft of the machine from 3 meters from the previous 6 meters for the SR2000. That gives us a lot more flexibility around the choice of final assembly location, and particularly around load out from those locations. While we've got a very kind of a radical looking innovative device, we've managed to adhere to quite standard steel fabrication grades and welding techniques, such that we can engage with a wide variety of existing metal fabricators for the development of the O2 tidal turbine. And we've demonstrated that our fabrication scope can be executed actually for the most part with SME enterprises right across the UK and Europe. So again, I'm going to focus on the next slide just on the primary build contractors that were associated with the O2 tidal turbine. So for the O2, we've achieved around 75% local supply chain content, so UK supply chain content associated with the build of this first O2. And we feel that's it's really critical for both societal acceptance for tidal stream energy, but also for enhancing the case around revenue support for the technology as well. While we've got loads of brilliant European research and supply chain partners, I think that is really critical, because one of the missing pieces of the jigsaw is that national revenue support for the technology. So we've worked with companies such as Gray Fabrication in Fife, who are based inland in terms of the fabrication of the steel sections for the platform. We've worked with Fawn Trackway down in Wales on the anchor structures for the machine, down to Southampton, at Gosport, where AC Marine Composites supplied the blades for the machine. A number of other notable suppliers were Texo Group in Dundee, where the main turbine manufacturer was carried out and the turbine launched, and then Leask Marine, based in Orkney, who have carried out all the vessel operations, both involved in towing the machine to Orkney and the installation of the anchoring cable systems and in the installation of the device itself next month. So all in all, we've calculated that we've generated around 70 full-time equivalent direct and indirect jobs associated with the O2, and as I say, between 75 and 80% UK supply chain content associated with the O2 tidal turbine project. So we're very much proud of that as well. Moving on then finally to next steps. Over the next 3 years or so, we've got, we've put in place a significant budget for prioritizing ongoing cost reduction innovations in our technology. Areas we're looking at are particularly on increasing rotor sizing, drivetrain sizing, doing away with expensive ballast style anchors and moving towards rock drilled anchor systems, much more advanced pitching systems as well. So we think that over the next 3 years alone, through innovation, we could reduce the generating cost of our technology by a further 25%. We'll also be working with the supply chain, capacity building towards first arrays in Scotland and in the UK. We'll be working closely with EMEC and others on environmental monitoring, as we hope to have more devices in the water, more data coming back. We will look to do more sophisticated environmental monitoring on our floating platforms, which, being highly accessible, are very amenable to mounting of environmental monitoring hardware as well. And then I guess, as a number of you will already know, one of the missing pieces of the picture is on revenue support, and it's crucial that we see appropriate revenue support coming through for first commercial arrays in the UK. So along with the rest of the industry and the Marine Energy Council in the UK, we've been looking for essentially a ring-fenced minima for tidal stream energy in the AR4, the allocation round 4 auction that we understand is to launch in December of this year under the contracts for different system, and an administrative strike price of £250 per megawatt hour for first 100 megawatts of tidal stream projects. That will allow the first commercial projects in the UK to come forward, to allow us to continue to invest in reducing our costs through both innovation and supply chain learning. So I hope that's given you a very fast and brief, but hopefully useful overview of how we see the industry developing, what our challenges are, and the progress we've made to date. Thank you very much.
Thank you very much, James. That's great to see all the exciting developments happening there. I'm going to pass straight over to Cameron for our last presentation of the day. We're running over already, but if anyone does have any questions they want to ask the panelists, please do pop them in the chat and we'll see if we can squeeze some in at the end. Thanks, Cameron.
Yep, thanks a lot, Jonathan. Thanks, James. That was a great presentation. It's a tough one to follow, and I guess as someone who is in the marine energy industry, we've been really impressed by what Orbital's been doing. Both from a technology standpoint, pretty much all aspects have been very impressive. Especially, I think your engagement with the public and the sort of media stuff that's been coming out. But anyway, I guess this is about my presentation. So I'm Cameron McNatt. I'm the co-founder and managing director at Mocean Energy, and I'm going to give you, I guess, our perspective on how we see wave energy, getting to scale. So Mocean Energy designs ocean wave energy converters. We were founded by myself and Chris Retzler. Chris was one of the co-founders and the principal scientist at Polamis Wave Power. My background is in naval architecture and software development. I'm American, but I came to Edinburgh to do my PhD at the University of Edinburgh. So I've got, and Chris also has a very good knowledge of the sort of workings of the university system within Scotland, particularly Edinburgh, and the amazing facilities that they have there. software. So Mocean has now grown to a team of 16 people. Our primary headquarters is in Edinburgh, but we also have an office in Aberdeen. We've been very successful with grant funding, particularly through the Wave Energy Scotland program. We're one of the 2 companies that have been awarded a stage 3 project through WES. That is somewhat of the focus of my presentation, is just giving our perspective on going through the Wave Energy Scotland program. So our secret sauce is software. So we've developed, and this is, I think, why we've been successful within the WES program, and what we continue to add to the industry. So we've developed our own proprietary software that generates shapes and runs them through a simulation to assess things like power production. We wrap that up in some sort of AI optimization. This is showing a particle swarm optimization. And then we build small scale models and test them in wave tanks. And we have used the Edinburgh curve tank and flow wave, I don't know, on quite a few times. It's been fantastic to have access to those facilities. And all of that provides learning back to the simulation and validation of the software. And what that helps us do is reduce things like the power to mass ratio. So the plot you see up here in the corner is comparing a motion type geometry of a wave energy converter to a kind of very basic hinge draft. And I'm not saying this is the best design ever, but on the x-axis we have wavelength, and on the y-axis we have a measure of power per mass. And what you can see is simply by altering the geometry, we are able to dramatically increase the performance as measured by a power to mass, such that when you improve the power to mass ratio, the mass gets smaller, you're reducing the capital costs, and you're reducing the operational costs because these things are lighter. So just to tell you a little bit about the Wave Energy Scotland program from our perspective, where WES is really the preeminent wave energy development program here in Scotland and in the UK and in Europe in a lot of ways. So really our development through the WES program started at stage 0, which was the work that we did prior to entering the WES program and the work that we captured in our application. So even back then, back in 2015, we were going with this numerical modeling and optimization approach, and we came up with some, relatively crude hull forms that, and again, this is where we started to notice this trend. By changing the shape, we could improve power production. In stage 1, we've kind of further developed that design process. We came up with some more engineered type shapes, and we did some tank testing in flow wave. In stage 2, we then continued to further refine that optimization program and came up with this geometry through our optimization process, which again we built into a small scale model and tested in a wave tank, and that has ultimately enabled us to proceed to stage 3, which was to design and build our scaled prototype that we call Blue X. So you can see, how the design has changed and become more engineering, if that's a word, throughout this process. So we are currently in the Wave Energy Scotland Novel WEX Stage 3. We just finished the build of our Blue X prototype that was built and launched in Rosyth, so just down the coast from Orbital. Here it is sitting on the quayside. Here is some of our first wet testing, wet commissioning of Blue X in the water. And just this week, we are going to be loading the machine up onto a truck and transporting it up to EMEC to begin our testing there. We'll start our testing at Scapa Flow, and then we'll eventually move to the Billy-a-Crew test site, which is, very, very wavy and will be very exciting. In terms of products, what we're focused on in the near term is a smaller scale wave energy converter that we call Blue Star. So it's still a hinge draft with an innovative geometry, but we've added solar panels to it. And what Blue Star will be used for is providing power to subsea equipment, primarily in the oil and gas and offshore energy sector. So it provides power to what we call subsea tiebacks, where currently power is provided by long umbilical cables that are very expensive. We're talking a sort of £1 million per kilometer. And so the value proposition there is just that power is really hard to get to these remote locations. Another application is providing power to residential robotic systems, such as autonomous underwater vehicles, where the idea there is that if we can provide a power and communications link, we can leave these systems deployed so that they can carry out repeat operations. So Blue Star is focused on delivering not a huge amount of power, but really consistent power. And we address that with wave energy, multiple renewable energy sources, wave energy, solar panels, and battery storage. Through that initiative, we are also running a project that we call Renewables for Subsea Power with some really great project partners, including ECOG, Harbor Energy, Modus. So ECOG is providing a subsea battery system. Harbor Energy is an oil and gas operator sponsor. Modus is a subsea systems or subsea survey company. They're providing the residential AUV. Baker Hughes is providing some what are called subsea control modules, and the project's sponsored by OGTC. So last year we completed a feed of this project, and this year we're doing phase 2, which is to build all of the subsea kit. And then next year we will integrate this with our Blue X wave energy converter that was developed through the WES program and redeploy it offshore to demonstrate providing power and communications to subsea equipment. But our strategy overall is really to start small, go big. So right now we're focused on our Blue Star wave energy converter, where I've already talked a little bit about what that's for. A lot of people refer to these as niche applications or niche markets, but when you really look at the market for subsea umbilicals and subsea power, it's billions of pounds. I mean, these niche markets aren't really that little. And developments within this market, our design process is very scalable. All of the developments will provide learning and hopefully will generate a bit of revenue, which can be reinvested towards our larger scale product line, which is Blue Horizon. So we're focused on developing a 250 kilowatt machine in the near term, and that will eventually result in a 1 megawatt machine. And just as we found applications in sort of off-grid markets for Blue Star, there are numerous applications for Blue Horizon as well, including powering offshore platforms, providing power to remote and island communities, and ultimately we see our larger scale Blue Horizon, rather than competing with offshore wind, where the offshore wind is very established, we see combined wind and wave farms, maximizing the utility of the space around these farms. So just to talk a little bit about, what are the benefits of large scale wave energy, and maybe I won't dwell on this too much, but first of all, it's providing a balanced supply. So we really need all forms of renewable energy to ensure that we can provide a consistent supply of renewable power. And so these plots over here on the right, they're from another wave energy developer, and they're just showing the seasonal variability of wind, solar, and wave. And wave, the green line, is very complementary to wind and solar, and that's true on a sort of day-to-day time scale as well. Wave energy is highly predictable, so the large swell waves were generated by storms that occurred way out in sea, and you can predict the arrival of these waves, up to a week in advance. And as I mentioned, we don't really see necessarily competing against wind and floating offshore wind, but really more combined wind wave farms where we're fitting wave energy converters in between the large gaps between these floating turbines. The market for wave energy is really huge. I mean, we say things that sound a bit trite. It's the largest untapped energy resource and renewable energy resource in the world, but it's true. It's something like 1,800 terawatt hours of accessible wave energy per year, which would be about 80% of the worldwide electricity supply. As I mentioned, there are numerous non-grid applications, the subsea tiebacks, offshore platforms, marine aquaculture, et cetera. And we're seeing, you know, as Jonathan pointed out, and some really ambitious ocean energy targets set by the EU, by the US, and globally by 2050, gigawatts, hundreds of gigawatts. And so our point now is, you know, where we are now is if we were given a budget to build a megawatt scale machine, our first of a kind LCOE is projected to come in around 318 pounds per megawatt hour, which clearly is tough to compete against other forms of energy. But what it does is puts us near the bottom end of the range of the industry scale. And we believe that with our, you know, learning by doing at smaller scales and by our structured design process, we can continue to have sort of best in class learning rates and rapidly improve our LCOE, such that by 1 gigawatt of industry deployment, we think we should sit at an LCOE of 117 pounds per megawatt hour, you know, a little more, a little less, which should be very competitive and should hit the targets that have been set by the SET plan, I believe. And that's me. Thank you very much.
Thank you very much, Cameron. That's really great to see the progress happening through those slides, and exciting to see the deployments coming up. We're already running over time, so I'm just going to ask two really quick questions, one to Cameron and one to James. Cameron, it's really great to see that last couple of slides of your where you think you are on the LCOE curve and the trajectory you think you're going to take down there. You mentioned deployment, and you mentioned you know, learning through doing, and a lot of the extra innovation I mentioned earlier is already being built into your technology through the innovation program that you're supporting. But what do you see as your main challenge of getting down that curve? Is it time in the water and deployment, or is it a technology and innovation?
I think it's got to be a bit of both, Jonathan. I think we've really got to get in the water and you know, demonstrate performance. I mean, performance, I think you can demonstrate pretty rapidly, but it's building that track record of reliability and survivability that we've heard so much about is key to just and you know, kind of figure out the you know, the unknown issues, the things that you didn't expect. I think from a technology standpoint, it's probably the power takeoff system. So we've you know, really we've developed our hull forms, but they're just steel. I mean, not to say that it's simple to fabricate, but it's pretty well understood. The biggest challenge is the big hinge, where we need a lot of torque, and it's a slow reciprocating motion. And you know, I should have mentioned this. I didn't do a great job talking about the supply chain, but we worked with the so within Blue X, the generator was developed and provided by the University of Edinburgh. So it's their C-Gen technology that was custom built for the Blue X machine. And we really, you know, there's no off-the-shelf PTO systems for wave energy. So it's really key to work with, you know, innovative universities and companies developing solutions around the power takeoff.
That's great. Thanks, Cameron. And a similar question to James. You're making nice steps through the increasing size devices, but what do you see as your key challenge between here and commercialization? Is it a technology one, or is it a deployment and increased scale of the sector? And is there a key subsystem that you think is the key innovation requirement in your technology?
Yeah, I think one of the key innovations we're looking at the moment in terms of the technology is on the anchoring system. We feel like with one fell swoop we could do away with, you know, up to £1 million of the capex per device by looking at that. There is going to be, you know, some scaling of the powertrains and the rotor blades. So, you know, blade testing is going to be very, very important to see how kind of far we can go on that. Though that won't be appropriate for every site, particularly where they're more kind of depth restricted. But I think, you know, what needs to underpin all of this is kind of line of sight to, you know, commercial projects. So I think we can't you know, you can't continue to invest in developing these innovations without line of sight to you know, to a commercial pipeline. So it is critical that, you know, we do see something over the next year or so in terms of provision for appropriate levels of revenue support for the sector. Because I guess unlike wave, I think the We kind of know where we need to go with the horizontal axis generators. We think with the floating platform, we've resolved a lot of the challenges around accessibility, particularly with our new structural configuration for the O2. While we'll see continued innovation on that kind of platform technology, we're not going to see any radical departures from that. So I think we know where we need to go. We've been working very closely with Black & Veatch over the last 12 months or so in mapping out our cost reduction pathway through innovation and what the priority cost reduction innovations need to be. We just need to see that line of sight to commercial projects and appropriate levels of revenue support. And we don't necessarily need to see line of sight to revenue support for the first gigawatt, even just the first 100 megawatts of projects. We feel we can make major cost reductions over 1 to 200 megawatts of installed capacity. So that's what we're really working with the industry towards advocating for over the next year or so, particularly with UK government. We recognise that there are other parts of the world, particularly like Nova Scotia, where they have put in place appropriate revenue support for the sector. But I think it would be remiss when, as you say, the UK has such an abundance of both tidal and wave resource for there not to be appropriate levels of revenue support in place to kind of grow this home market for the technology.
That's great, James. And I think you're exactly right. And it's a very exciting time for the sector with both of your upcoming deployments. So I wish you best of luck with the deployments coming up soon. And we're over time, so I'm going to wrap up the webinar there. But I'd just like to thank all my speakers very much for joining us on the webinar. I think that was a really interesting run through the Scottish opportunity, the global opportunity, and then the support mechanisms, both research and funding, and then 2 really exciting projects at the end there. So thank you very much. Thank you very much for the ETP for hosting us, and I look forward to seeing the rest of the ETP Emporium webinars coming up. Thank you very much, everybody. Thanks for attending.
Thanks, everybody. Bye.
Thanks, everybody. See you in a couple of weeks.